Now we are going to implement the file manipulation features in the Pintos operating system. There is a process descript table, and this is process descriptor. It's a struct thread. And in a thread, it has to have a pointer that points to the process descriptor table. Now, process descriptor table is an array of pointers, and each entry in the array points to the file object. So first one is standard input. The element 0 contains a pointer to the standard input file structure, and element 1 points to the file structure for standard output, and the index 2, the second element, the process file descriptor table, points to the standard error. And then there is file descriptor entries here. So current Pintos does not have file descriptor table, so we have to implement it. This is the details of the implementing file descriptor table. Each process has its own file descriptor table. We're going to define maximum size of 64 entry. File descriptor table is an array of pointer to the struct file. Pointer to the struct file. So there's going to be 64 entries, and each entry points to an object called struct file. This is 0 and this is 63. And FD is file descriptor is an index of the file descriptor table, and it is allocated sequentially from 0 to end. And file descriptor 0 and 1 are allocated for standard input and standard output respectively. And open system call returns a file descriptor. So open system call allocates a struct file, and it scans whatever empty entries on the file descriptor table, and then sets the associated entry points to the struct file that is open. Close system call resets the value of an entry with 0, so it resets the pointer. This is the sample layout of the file descriptor table. We are going to define the file descriptor table of 64 entries. The first approach is directly embed the file descriptor table at the thread structure 64. Or we can add a pointer to the file descriptor table, and then we can allocate separate file descriptor table at the kernel memory area like this. And then in this case, the two threads can share the same file descriptor table. Or here, in this example, thread A has a file descriptor table here, and then it contains a pointer that points to its own file descriptor table. And thread B has its own file descriptor table defined outside the thread structure, and file descriptor table pointer of thread B structure points to its own file descriptor table. When the thread is created, the operating system allocates the file descriptor table for a thread, and then it initializes a pointer to file descriptor table. One thing we should not forget is when initializing file descriptor table, we have to reserve file descriptor 0 and file descriptor 1 for standard input and standard output. When a process is terminated, it has to close all files, and then the operating system deallocates the file descriptor table. One thing we have to emphasize is the race condition. In Pintos, we are going to use the global lock to avoid race condition in the file. So we are going to define a global lock, and then whenever file system related system call is executed, it is protected by the lock. This is to avoid the race condition of the file system operation. We have to modify the page fault for the test. In Pintos, some test checks whether your kernel handles the bad process properly. In Pintos, it needs to kill the process and print the thread name and exit status -1 when page fault occurs. But for this purpose, we have to modify the page fault to satisfy test requirement. And simply, you can call exit -1 inside page fault. These are the system calls related to file manipulation. First one is create. it creates a file of whose size is the initial size. And there is system call remove. It removes the file whose name is file. And open, and it calls file system open. And remove, it calls file sys remove. And create, it calls file sys create. So all these functions are already defined in the Pintos. So what you have to do is just provide a certain appropriate system call that calls this function. There is a file size function also, and it calls a function file length. In read system core, you have to distinguish the read from the file descriptor 0 and read from other file descriptors. In case the file descriptor is 0, then you have to call the input get C that reads the characters from the keyboard. And for other file descriptors other than 0, you call file read. Same things applies for write system core. When the file descriptor is 1, then you have to write the outputs to the console. Otherwise, you have to call file write to the write. And there is a function called tail, and it calls file underbar tail. And there's a system called close, which close the file underbar close. The last topic you have to take care of is that denies the rights to the executables. What if the operating system tries to execute a file that is being modified? Then the result cannot be unpredictable. So the objective of this topic is do not allow the file to be modified when it is open for execution. There are two approaches. The approach is that when the file is loaded for execution, call file deny write. When a file finishes execution, call file allow write. So at the beginning and end of load executable, you call file deny write. When process exits, you add file allow write. Using this approach, you can simply enable the Pintos to deny writes to the executable file. Once you completely implement all these features, then you'd be able to pass the test. I would like to finish this presentation by summarizing what functions you have to add and what functions you have to modify. These are the call flows of the Pintos operating system in creating a process. First, it calls process execute, and then process execute calls thread create. And then it calls start process, and it calls load. So at each process, you have to provide a feature to parse the name of the program to run. And then here, you have to create a thread and add it to the ready list. So new thread is created here, and it's put it in the ready list. But interesting thing is, until this point, you don't know which function or which program you need to execute. And then at the start process, it prepares an interrupt frame, and it prepares an interrupt frame so that it can get into the user mode from the kernel mode and start executing. And then it loads the executable. And then if all this succeeds, then you execute the user program. Good luck.